Every voice holds a soul. But what happens when a machine learns to speak it? This isn't just audio data. This is identity, rebuilt from pure sound. When AI can speak like anyone, truth itself becomes optional.
The source: finding the vocal blueprint. The journey begins in the digital wilds. Perhaps it's a CEO's earnings call, a popular streamer's 3-hour gaming session, an audiobook narrator's crisp performance, or a simple 30-second voice memo you recorded in a quiet room. This audio is the sacred text, the raw ore from which the vocal essence will be mined. The quality here is paramount. Studio quality audio is gold. A phone call recorded in a windy cafe is rough iron. The AI will work with what it gets, but the final fidelity is decided in this very first step. Data harvesting, the great ingestion. The chosen audio files are uploaded or fed into the cloning platform servers. This isn't just playing a recording, it's a systematic ingestion. The system strips away metadata, identifies the primary speaker if there are multiple voices, often isolating the target from interviewers or background chatter, and prepares the audio for its digital autopsy. It's gathering all the clay from which it will sculpt a new, synthetic speaker. Digital dissection, slicing sound into atoms. Here, the continuous river of speech is broken into its constituent molecules. Using algorithms, the audio is segmented into units as small as 10 to 50 milliseconds. Each segment is a minuscule snapshot of a vibrating vocal cord, a tongue hitting teeth, a puff of air. This process, called windowing asterisk, creates thousands of these frames. Imagine dissecting a spoken sentence into a flipbook where each page is a sliver of sound. This is the R's flipbook. Finding patterns, the neural network listens deeply. This is where their EAI truly awakens. A deep learning model, often a type of recurrent neural network, RNN, or transformer, like the architecture behind models like Valley or your TTS, begins its analysis. It doesn't hear like we do. It converts each audio slice into a spectrogram, a visual map of frequencies over time. It then looks for patterns. Asterisk, how does the frequency distribution shift when this person says EO versus ER? What is the exact shape of the resonance when they pronounce their ERES? How long, on average, is the pause between their phrases? Asterisk, it's building a statistical profile of a voice's behavior. Learning the code, creating the vocal DNA. The R's goal is not to make a perfect copy of the audio it was given. Its goal is to learn the rules that generated that audio. It distills everything it has learned into a complex, multidimensional mathematical construct called a latent space or a voice token. This is the vocal DNA, a compact, numerical representation of the speaker's identity. This model contains no actual audio. It contains the instructions for generating audio that will sound like the speaker. The original file can be discarded. The ghost is now in the machine. The teacher model, a master of generic speech. Rarely does training start from zero. Companies use a massive, pre-trained foundation model that has already consumed tens of thousands of hours of speech from hundreds of thousands of speakers. This teacher already knows the fundamentals of human phonetics, grammar, and prosody in dozens of languages. It understands the universal building blocks of speech. Think of it as a master sculptor who knows human anatomy intimately. Specialized training, the apprenticeship. Now, the unique voice data from Step 1 is used to fine-tune this generalist model. It's a focused apprenticeship. The system runs the new audio through the teacher model, compares its predictions to the actual audio, and minutely adjusts billions of internal parameters. With each iteration, it's answering, how does this specific person deviate from the average? How is their vocal tract shaped differently? The model becomes a specialist in you. Phoneme focus, the alphabet of sound. The training drills down to phonemes. The tilde are 44 distinct sounds in English, e.g., the aspirated pin a pin, the nasal nin a no, the vowel air in a cat. The model learns a precise map. E for this speaker, the phoneme E, as in bit, has a slightly higher fundamental frequency and a tighter spectral tilt than the average person. It's learning the speaker's unique accent and articulation at the most atomic level. Emotion and nuance, capturing the soul of speech. Advanced systems go beyond words to prosody, the music of speech. They analyze. Pitch contours. Does their voice rise hopefully at the end of a question? Stress patterns. Which syllables do they naturally emphasize? Rhythm and tempo. Do they speak in rapid-fire bursts or measured cadences? Breathiness and vocal fry. Does their voice trail off with a breathy sigh or crack with casual fry? This layer captures the speaker's idiolect, the unconscious, personal style that makes a voice emotionally recognizable. The voice clone is born, the digital puppet. After hours or days of computation, depending on the power, the fine-tuning converges. The result is a standalone, lightweight model file, the voice clone. This file, sometimes only a few megabytes in size, is the final product. It's a digital puppet, a vocal avatar. It contains all the learned knowledge of how to imitate a specific human voice, waiting for a script to bring it to life. The script, writing the new reality. The user types, or pastes, text, the stock market will crash tomorrow. I love you, Grandma. Please wire the money to this new account. Or simply, a welcome to your audiobook. This text is the command, the spell to be cast by the cloned voice. The intent can be benign or malicious, but the technology is indifferent. Text to phonemes, linguistic breakdown. Before sound comes language analysis. A text-to-phoneme model or forced aligner breaks the script down. It doesn't just see the word through. It converts it to its phonetic transcription, AU. It also adds linguistic markup. This is a verb. This word should be stressed. This comma indicates a clause break. It creates a detailed choreography sheet for the voice clone to follow. The generation engine, waveform synthesis. The core cloned model now activates. Using a technique like diffusion, which starts with noise and iteratively refines it toward the target, or autoregressive prediction, which predicts the next audio sample based on all previous ones, it begins to generate raw audio. It queries its internal vocal DNA constantly, a given that the last sound was 8, and the speaker's model shows they aspirate it lightly, and the next phoneme is a long oo. What should the precise waveform for the microsecond time t be? Making choices, the probability dance. This generation is a vast series of probabilistic choices. At each step, the model calculates a probability distribution over all possible next microsounds and selects the most likely one based on its training. It's walking a tightrope between faithfulness to the text, saying the right words, and faithfulness to the clone's identity, sounding like the right person. The raw output, a robotic foundation. The initial audio output is often stark and unnatural, a monotone, correctly sequenced string of phonemes. It has the right of voice color, but none of the fluidity of life. It sounds like a very accurate but emotionally flat text-to-speech engine. This is just the skeleton. The vocal conductor, the prosody model. A specialized post-processing network, sometimes called a neural vocoder or a prosody adapter, takes the skeleton and adds the muscle and skin. Its sole job is to make it sound human. It injects naturalistic pitch variation, adds micropauses in places a human would breathe, and smooths the transitions between phonemes so they flow, not click. It's the director telling the flat performance where to add emotion and rhythm. Emotion injection, the dial of feeling. On command, The user can twist a virtual dial. A sadness, 70%. A energy, 90%. The model adjusts its parameters accordingly. For a sadness, it might lower the pitch range, slow the tempo, and add a slight tremolo. For a excited, it would raise pitch, increase tempo, and amplify dynamic range. This is where creative or manipulative control reaches its peak. Error correction, polishing the artifact. No AI generation is perfect. The system runs final checks for common artifacts, adversarial noises, strange digital whistles or glitches, phoneme repetition, a STS to stutter, or unnatural plosive bursts, overly sharp APR and ABA sounds. Filtering algorithms and the outlier detection models smooth these out, replacing them with more probable, cleaner audio. The final render, the illusion is complete. All components, the generated waveform, the refined prosody, the emotional tuning, and the cleaned audio, are mixed and rendered into a standard audio file, like a .wav or .mp3. What was once a silent string of text now exists as a spoken utterance. The voice that never said those words has now said them. The new reality, the voice is unleashed. The audio file is downloaded, shared, or integrated. Its journey concludes in the real world. A customized chatbot greets a customer. A historical figure narrates a documentary. A filmmaker rescues a scene with flawless ADR. A scammer bypasses voice authentication, or a loved one receives a call from a voice that isn't there. The circle closes. The voice, once a unique, biological signature, has been abstracted into code, remixed, and reborn, a testament to human ingenuity that simultaneously dismantles one of our most fundamental pillars of trust, the sound of another person speaking.